finding these interesting. We certainly do. Again, if you have any questions, interrupt and ask the students. So without further ado, here's the next team.
Hello out there. Welcome to the Flexter. I'm Owen Mayhew. These are my associates, Bryan and Kevin Orth. We were tasked by Woody Blake Company. They are a cable producing company. We make cables for military, industrial, and medical, and custom applications, and they also do coil cable assemblies. So the task we were received was to design a mechanism to test the durability of the cables. And some of the features that we were tasked with putting in our design were the ability to flex the cables to a specific angle repeatedly, oftentimes very repeatedly, several thousand cycles. It had to test different angles because sometimes the test called for a different non-flexion of the cable. Also, it had to be able to test 10 to 20 cables, and it had to be able to detect whether a cable had failed, which would be one conductor in the cable failed, and that fails the whole cable. Also, to export into a database that's easily accessible remotely, so they can view the data and give it to customers. I'm going to turn it over to Kevin now.
Okay, this is an overview of our entire system. Each of these parts that I'm going to mention, we're going to explain further throughout the presentation. So, first of all, there's the cables being tested in orange. They hang from the cable flexing fixture, which is mounted to the frame by bearings. Their motion is driven by the crank rocker and pulley, which is powered by the motor and gearbox in black. The status of the cables is read by the data acquisition device during the test, which is connected to the cables by these wires in yellow. The tachometer in blue reads the speed of the machine and the number of cycles. The data from the tachometer and the data acquisition device are sent to the computer through USB cables. The computer saves the test data in a file and also displays the cycles and other information on the screen of the computer during the test.
So I'm Bryan, and I was responsible for the mechanical portion of this project. And actually our responsibilities are on this slide. Owen was responsible for the connector, and Kevin was responsible for programming the data reading and logging. So for flexing a cable, can we hear me? All right. So for flexing a cable to test durability, Whitney Blake's customers require cables to be tested for quality control. And the cables are tested by flexing them at one point on the cable for many cycles. And oftentimes, it's over 30,000 cycles, and these tests can take days or weeks. So if one conductor, as was already said, loses its continuity or breaks, then that cable has failed the entire test. So for our flexing design, we chose to go with a crank rocker system, which comes along with a motor and gearbox, and the crank on the crank rocker system has adjustable angles. So for design of a crank rocker, this is taken out of one of our textbooks that we used in class a couple years ago. Crank rockers are common for applications where repeated oscillations are necessary, where you might see a crank rocker. Often, they're actually pretty hard to see, but something like train wheels, the system that makes them go is very similar to a crank rocker, or your at-home fan oscillation system inside what makes that go back and forth and oscillate is very similar to a crank rocker. So the design of a crank rocker involves determining the appropriate lengths of 4 linkages to achieve a desired throw angle. And a throw angle is defined as the angle between the extreme positions of a rocker. And I have visuals for that in the next couple slides. So here's a simple, undefined example of crank rocker design. As you can see, the linkages are between points A to B, B to C, and C to D. Points A and D are for rotary, or they're for pivoting. So on the next slide, we have our 3D model with the linkages on top. As you can see, from the center of this flywheel is link 1, and this would be point B right here, and link 2 goes across, that would be point C, and the center of this pulley and rocker arm is point D. And this is our line diagram, which was done in SolidWorks. As was said in a different presentation, SolidWorks is a computer-aided design program that makes 3D models and line diagrams such as these ones. The top image here is the crank rocker in the initial start position. The two on the bottom are each of the separate extremes to one side. This is 30 degrees to one side for our 60-degree rocker angle, and this is the other position. So we go back to our 3D model, and this is what, from the line diagrams that I just showed you, is the 3D model that came from it, and it's just shown without the linkages on top. And this is the crank rocker that we actually made and fabricated. As you can see, there's no flywheel, and this is partially because of the materials that we had. To design the flywheel, it came out to be like a 10-inch diameter, and we didn't want to do that, so we realized that we could just put the lines, or the circles for the angle adjustment, just in one line, and we used some, just any aluminum that we had in the shop, and it worked out fine, it works great. And this is an example of a flex cycle. So right here, this middle line would be the cable fixture in an upright position, and it would go and flex to its desired angle on one side, and then it would flex all the way back to the same angle on the other side, and then back to the initial start point would be one flex cycle. And to make our flex angles and our rocker arm correlate together, we had to use a 3-to-1 pulley ratio. So our rocker arm at our largest test rocks to 60 degrees of a throw angle. And if we multiply this, our pulley here, as you can see, is 3 times the diameter of our smaller pulleys attached to our fixtures. And this is to avoid binding in our rocker system, because we don't want our rocker arm to be 180 degrees with the linkage that's in it, right? Well, you can't see it in this picture, but we can show you when we demonstrate. So with that 3-to-1 ratio, we multiply our 60 degrees by 3. That gives us 180 degrees, which correlates to our 90-degree test. And and same with this 40-degree one. We multiply that by 3, it's 120. That's our 60-degree test. And we also have one more, it's a 45-degree test. So this is our motor and gearbox. We got them off automationdirect.com. The motor runs at 90 volts DC at 1800 RPM, and it's also 1 horsepower, which is why our fuses keep blowing. So our gearbox is a 15-to-1 ratio, which brings our RPMs down to 120. So for every 15 rotations of the motor shaft, we'll have 1 rotation of the gearbox shaft. The reason why we needed 120 RPMs is because Whitney Blake's most common test is at 90 cycles per minute. So 1 cycle of the crank or 1 revolution of the crank is 1 flex cycle. So therefore, 1 RPM is going to be 1 cycle per minute. So Whitney Blake requested that our system be able to do between 20 cycles per minute to 120 cycles per minute. So with our variable motor control, we are able to do anywhere between 0 to 120 cycles per minute. We'll hand it over to Kevin.
The fixtures that Bryan was mentioning must be able to flex 10 cycles, or 10 cables on each fixture. There are 2 fixture types that Whitney Blake uses to test their cables. The one type, which we are demonstrating, holds nylon inserts, 10 of them on a fixture, and the wire is threaded through the insert, and as the fixture tilts left and right, the wire is bent, or the cable is bent over a radius on the bottom of the nylon insert, Another method to flex the cables is to bend them over rigid mandrels. Whitney Blake Company asked us also to improve on the way that the cables are secured to the fixtures. The current method is to just tie a knot and they hang right through the nylon inserts. So here are some concept models. They use draw latch clamps to secure the cables. I'll explain those in a minute. The left fixture uses nylon inserts. Those are the yellow pieces right here. And the black lines represent the cables that are threaded through them. This is a fixture using the mandrels. The cables are secured to a piece that moves back and forth, bending the cables over the mandrels. That part was not completed yet, but it has been designed. This is a draw latch clamp fixture that we designed. This prototype was 3D printed in plastic by BTC's Rapid Prototyping. The clamp works by holding the cable between the angle steel. First off, this is the cable here. It holds the cable between this angled piece of steel, which is pulled against this face by the draw latch clamp, therefore holding the cable in there. I have a video that explains this I would show you, but it's easier to see on the screen. These two pieces are separate on the fixture. This is where the nylon insert would go in this hole here. The cable's threaded up through it, through the draw latch. This is the metal clamp piece here. And you attach the draw latch to the top of this piece. You clamp it down. This holds the cable securely. There are weights. I'm explaining that there's the radius that the cable is bent over. There are weights hung from the bottom of the cable. And the fixture moves back and forth in that way. And there's 10 of them in a row, like that. This is a model of what the whole fixture looks like when it's assembled in SolidWorks. Notice this down rod right here is used to keep any of the draw latches from kind of popping up. This is what our completed fixture looks like without all the hardware.
All right, so another issue we had to address was how we were going to connect the cables in a expedient fashion that would produce a reliable connection so that we could get good data from the data acquisition unit we were implementing. In order to do this, we needed to make sure that there was minimal prep, so no crimping, no extra stripping of the wires at all, and hopefully the whole setup is inexpensive and fairly reliable. And we were planning on using a lever mechanism of some sort to expedite attachment of the ground because it doesn't fit in a traditional wiring connector. So you can see right here a typical cable produced by Whitney Blake, and it's got all sorts of parts. The most important is the wires here, the individual conductors that transmit the signals. Also, we have some drain wires here, which are ground for grounding equipment, so that it's all the same level. And that in this picture is just kind of wound into the shielding that normally would wrap all this up. We have some cotton in there for shape, and then also some nice foil here for shielding. So as you can see, we have a nice round connector right here, or round cable, excuse me. And the type of connector we chose to go with was a insulation displacement connector. That's what the IDC stands for. And it's designed to work with a flat ribbon type cable. And the reason it's called insulation displacement is you have these little knife blades here on the connector, and you insert the wires over these, and then when you press down with this, it pushes the wires onto the knife edges, and that cuts through the insulation, so you don't have to strip all the individual wires, and you can just clamp them all up at the same time. The trick is just lining them up, and that was one of the concerns we addressed with this. So this is our wiring jig, and basically it's got a bunch of little grooves that you can lay the wires in, and it's got a top piece that kind of flips down and connects. You can see where the holes in the bosses are, and there's a spot here for the connector. The connector sits in there. Put the wires in, put this down to hold the wires in place while you get them all lined up in the correct order, and then you can just put the other half of the connector in, and you're good to go. You have one terminated cable. So the other design issue we had to address with the cables was how we were going to interface them properly with the deck. And basically the way we decided to do this was to create a board that would terminate each end of the cable and loop the signal back through. Originally, we were contemplating reading each and every conductor, but that would have been prohibitive if we're doing a batch of 20 cables with 14 conductors each. That's 280 readings we'd have to be taking for each iteration of the chart there. So we ended up doing a series parallel where all of our conductors in a single cable were in series, and each cable was in parallel with the other cables. And it worked out pretty well. Also, for our interface boards, we decided to implement an LED so that the operator could verify that they had hooked everything up correctly, because it would shine the LED. That if the cable stops conducting, the LED turns off. So here's just what I mean by series parallel. So this would be an example of one cable here, and then you'd have some sort of mechanism on each end, and you have your signal going through, and the boards on the end would loop it back through. So you only have to have one ground and one reading, and that makes it pretty easy to do a whole bunch. So here's the boards we designed in EagleCAD. It works pretty simply. Basically, this pin is an input for the DAC, and it's always pulled up with an internal Orth resistor to the 5 volts, and then that is unless, of course, you short it to ground, which happens if the cable is conducting all the way through. So there's a jumper here for even number of cables. If there's an odd number of, or even number of conductors, if there's an odd number of conductors in the cable where you want to test the shield with an even number, this is hooked in to the shield, and then on the bottom connector here, connect back out. There's also jumpers to size your system appropriately. If you only use the first six pins, then you'd put in a jumper here on the fourth one, and that would allow you to complete your circuit. There's our LED we were talking about earlier. In addition, well, once we got these schematics, it was pretty easy to use ELM, which is just basically a computer design program for designing circuit boards, to get our design planned out here, and then fabricate a prototype. So that was what we did with the cable wiring. Here's Kevin with the data acquisition.
So I had to design a program that would be able to use presets for each test, so you don't need to set up each test manually. It also had to display a tachometer reading of the system so that you could see the speed and adjust the speed if need be. It also had to record the continuity of the cables throughout the test and save that data in a usable format. We chose to create a program using LabVIEW, which is a graphical programming software, because it's easy to troubleshoot, and National Instruments provides excellent support for our client. And also the external hardware that works with the program is easy to replace and purchase. So to read the cycle rate of the machine, we programmed an Arduino microcontroller. The Arduino is programmed to read a pulse with a 45-degree tab. This is the front of the gearbox here. This is the output shaft. There's a tab that's exactly 45 degrees connected to it. The tab passes through this optical limit switch here, which creates a pulse width. And depending on the speed of the output shaft, you read the pulse width here in milliseconds. So to get the rotational speed of this output shaft in RPM, since 45 degrees is an eighth of a rotation, you take the pulse width in milliseconds, multiply it by 8, and divide it by 1,000 seconds per millisecond, which gives you the rotational speed of the shaft in seconds per rotation. And to transfer that into RPM, you just take the number that you got and divide 60 by that number, which cancels out seconds here and here. And you end up with minutes per rotation. Or rotations per minute, sorry. Rotation ends up on top. The Arduino, which is a microcontroller, is programmed with C. As was mentioned earlier, it's a line-by-line programming software, or programming language. This program is uploaded to Arduino from the computer, and the Arduino runs it separately. It's not run on the computer. The Arduino then sends LabVIEW, the cycle rate that it reads, and the cycle count through the USB cable that was on the system diagram. We used an Arduino instead of a digital input on our DAC system, or our data acquisition device in LabVIEW, because LabVIEW is not designed to measure things like frequency and pulse width. It's quicker and more reliable to make these types of measurements on an external device and then send that data to the computer. National Instruments does supply extremely precise devices which do this and communicate with the program, but they're very expensive, and the Arduino was readily available, and it gives us the precision that we need since this device doesn't go much more than 120 RPMs. This is what our data acquisition block looks like. It's from National Instruments. It has 24 digital inputs on each side. There's 12 on each side here. There's screw terminal connections. And it sends LabVIEW the state of all those inputs through a USB cable up here. This board right here is just I'll show it to you during the presentation of the machine. But this is just an example where we were testing the inputs. So we were using these small cables to represent a whole cable that would be being tested. So I had to come up with a preset file format, which could be read by the program. This file would be written by the user, and the file is selected in the program when you run it, and all the test parameters that you typed into it are loaded to the program, as well as the output file name of your test add, whatever you want that to be. So this is what the front panel of our user base looks like up here. It shows the contents of the preset file, and again, those contents over here as they were extracted from the file. It also shows the current cycle rate of the machine in a gauge and numeric form right here, and it also shows the cycle count right here. This big red LED display is an indicator warning the user that the cycle input, or this current cycle rate, does not match the cycle rate that was input by the file. Since there is no feedback from the program to the motor controller, we decided to do that manually. It also displays the status of all the cables. There's only 3 here for prototype purposes. The rest of the channels can be easily added. This here is an example of what the graphical block programming looks like that I was describing. There's different blocks that do stuff and we line them together. It's much easier to troubleshoot than line-by-line programming like the C language. So this is what our output file looks like. It's hard to read those numbers, but it's not necessary to. It contains all the data from the preset file right here. It also has the status of all the cables at each cycle. This column right here is the cycle that the machine was on. This is the cycle rate that the machine was running at for each cycle. And this is the status of each of the cables. This is cable 1, cable 2, and cable 3. You saw on the display in the front panel there. A failure comes up as a 1 in the data. Right here. This column is cable 1. And the program also puts a note on the side of the data so it's easy to find. So one of the requirements was that the data could be accessed from anywhere at any time. So what the program will do is save this data in a Dropbox folder. Dropbox is a free file sharing program, and it automatically updates information put in the folder that's on the computer to the internet, and that information can be accessed from any device. And Bryan.
All right, so this is our budget to date. And as you can see, there was, we estimated that our project would cost about $3,500. And you can see what we bought and where we got it from on the chart and how much it cost. Whitney Blake gave us a budget cap of $5,000. And we only spent $3,335.09 so far. We did pretty well. So we would like to thank Roger Howes and Mike Wright for helping us out in the shop and giving us some good hours. They stayed during one of our breaks to help us out. We would like to thank Bob Royce for letting us into the calibration room every single day. And we'd like to thank Rick Ramlin, who is here from Whitney Blake Company, and their company as well, for being patient with us. They have hosted us more than once, actually, I think about 3 times. And he also came to visit a couple weeks ago. And they were... And they were very lenient, and they were very patient with us, and they were very helpful during the design process and getting all of our materials that we needed. And it was really great, and we'd like to thank our instructors as well. And now we'd like to open it up for any questions you may have. Go ahead.
What's the horsepower of that motor?
That horsepower is rated at 1 horsepower. It's 1. That's just the, well, you want to?
The original design used much larger fixtures because we were doing the mandrel type system, and the original one had really long levers, and we expected they were going to be much heavier than they ended up being. So we ordered the motor and gearbox pretty early in the design process, so it ended up being much larger than normal. But this is good because it's going to last a long time, so that's why we just kept that motor.
Have you thought about balancing it? Do you have any problem with the fact that your flywheel is not a flywheel and not balanced? Does it work okay?
We don't have balancing problems only because the gearbox there is a worm gear drive, which means there's very little backlash and it's very stable.
Early on, when Bryan was talking about the different angles of flexing, how do you switch?
Right now, we were hoping to just do a wing nut with our, we actually have these special, I call them fisheye joints, ball joints, which we can point out when we do a demonstration. Basically, it just requires you unscrewing a nut, replacing the linkage into a different hole, and just screwing that nut back on. Yeah, these golden pieces up here are the ball joints, and on the back side of that is a nut. And you just unscrew that nut, and you remove the ball joint from the crank, and then you just put it into a different angle hole and screw it back on, and you're ready to go. Hold on. Do you want to try and understand the question? Is the setup of the machine? Well, you got to plug it in. You've got to, with our variable motor control, you just have to set the speed, and it's just a dial. You just set it to whatever you want, and then you run it, and LabVIEW will tell you your speed and your cycle, and it's that easy.
Correct, yes. Because of the number of cables that have to be set up, 20 at a time, you're doing 40 connectors, you're crimping with those little things, and even with those, making it easier than individual solder joints for each one, it's still going to take a while.
Presumably you're trying to see if you can ALM aptitude. Are you concerned about connectors being reliable enough to start in this? This one end presumably is being reliable.
The connectors are taped down, so there's not really any changing stress on them during the course of the thing, in the course of the cycle. So we're not as concerned about that as the cables themselves.
Yeah.
Okay, basically, the smaller boards that you saw earlier, those are going on the top, and as long as you're testing an even number of cables, it just loops down to the bottom where it doesn't move very much, so you don't, during a cycle, the whole weighted portion on the bottom of the cable where we have the larger boards only shifts up and down about like a fraction of an inch. So we figure with a long enough span, and the connectors that we did with that insulation displacement actually aren't being utilized for those connections. I hope I answered your question. Yes, and the upper fixtures are grounded with a strap in the front. Ben,
How do you reset the cycle counter on the Arduino?
I'll let Kevin handle that.
We just use the reset button on the Arduino to reset the cycles. Eventually, I'll run a line over to the Arduino from the DAC using one of the output pins, digital output pins, because we're using 20 of the 24 input pins for the DAC. And we use 4 of those for whatever you want. So eventually, when you start a new task, one of those will go to the Arduino and tell it to reset.
Is the cycle count held in RAM or on the EEPROM permanent storage?
It's held in RAM on the Arduino. thing you could do, well, the motor would shut off, so it wouldn't be testing anyway. But one thing you could do if you were worried about that, the Arduino could run off a 5-volt supply, and you wouldn't have to have the computer running to get the cycle count, but you wouldn't get any data from the cables. So if you absolutely had to run a test where you weren't taking data in from the cables, you just wanted to flex it for a long time and see if any broke, you could run it with the computer off, and the Arduino would keep track of how many times it cycled. Anybody else?
The interested in failure analysis when one fails for whatever reason? Is that
Not particularly. Afterwards, they'll test it with an ohm meter occasionally to see which of the conductors failed. Mainly what they wanted to know was their current method hooks all the cables that are being tested in series. So if any one of them fails, if any one of the conductors inside any one of the cables fail, the entire machine shuts off, and you have to check each cable, each conductor in each cable to see which one actually failed. So this checks all the cables at once, so if one cable fails, you can just check the conductors in the cable. But they do an overreading of what the conductors are, what the resistance of the conductors is before and after the test.
Is there any concern with the shield breaking, failing?
Yeah, there is, and that's why it's part of the test. It just can't connect to the installation displacement connector because it's too many wires. So there's a separate screw terminal connector on the board for that. But usually it's a conductor that goes before the installation.
How do you decide which one takes on the components?
We just decided what each of us like about the project. Basically. I like programming, so I did the programming. Owen likes soldering, so he did the board. Bryan likes things that go